I'm Miss Erin, and this is my partner, Mr. Joseph.
Hi, and we're from UT, and we're here to teach you some more science. So today I brought with me a very cool toy, and it's called a Magnetrix toy. And so I'm going to show y'all how it works. So I have two different rings. That doesn't happen. So I placed one, and now I'm going to place the other one on top. Cool. So what happened?
They stuck together.
Yeah, they stuck together. So now what I'm going to do is I'm going to flip this yellow one and I'm going to turn it this side. Watch what happens.
It's floating.
Cool, it's floating. So it turns out that these different rings are made out of a special material. What do y'all think that material is called? Or what do you think they are, these rings?
Magnets.
Yeah, that's correct. They're called magnets.
This activity is going to lead us to our question of the day, which is, how does magnetism relate to forces?
Okay, so now that we saw our Magnetrix toy, we are going to pass out smaller magnets, and I want you to go ahead and try to replicate what happened up front. So try to pull off the same procedure with your magnets as what happened with the toy. I will give you some time to do that.
All right, hook 'em.
Horns.
Table 1, what did you discover about the magnets that we gave you?
There's an S and an N on them.
That's right, there's an S and an N. What do you think, Table 1, that the S and N stand for?
North and south.
North and south. What happened when you put the two north sides together?
They repel or don't want to stick together.
That's right, they repel each other. So just like in the Magnetrix, these two magnets repelled each other, and that's why it floated. What about when you put a north and south together?
They stick together.
They stick together. They attract one another. What else do you know of that has a north and a south?
Earth.
That's right, the Earth. The Earth has a magnetic field at north and south, and that helps us to use compasses to find direction. Now we're going to take up the magnets. My partner's going to take up the magnets. Now the type of force that magnets use is a special word called magnetism. Can everybody say magnetism?
Magnetism.
Good, magnetism. We're going to pass out a vocabulary so you can write down the term for magnetism. For today's activity, we're going to be split up into three groups where you will explore different parts of magnetism and magnets. Just like we did a few weeks ago, we are going to rotate clockwise. Table 4, what direction are we going to rotate?
Clockwise.
That's right, we're going to rotate clockwise. So now we're going to pass out our worksheets, and we are going to go to each of our stations. Tables 1 and 2, you guys are going to go to the first station. Tables 2 and 3, you're going to go to the second station, and everybody else, you're going to go to the third station.
So before we begin and split up into different groups, we are going to pass out job cards. So remember to get a different job card than you did the last week. But don't worry, we're all going to work together as scientists to explore what different properties of magnets.
Station 1. So I want you guys to remember back to when we did the Magnetrix. What did we say was causing them to be pushing away from each other?
They repel.
They repelled. It was a type of force. What did we say the force was called?
Magnetism.
That's right, magnetism. So we're going to actually learn, what else do you know about, what other things do you think use magnets in your everyday life?
On the fridge.
On the fridge. What else? Who's ever been to the doctor?
MRI machines.
That's right. If you've had something really serious, you might have to use an MRI machine, which uses magnets to be able to look at parts of your body. So we are going to look at a compass. And what do you notice about a compass?
There's different directions.
That's right. It's different directions. What direction do you think the red part of the arrow is facing?
I don't know.
No idea.
It's facing north. So which direction do you think the white part is facing?
South.
South. Great. So we're going to take some magnets, and I want each one of you to take one of these magnets and put it right next to. Let's do the south side and put it right next to the compass and see what happens. Only hold it there for a few seconds. What did you notice happened?
The right side went to it.
That's right, the right side went to it. What about if you flip your magnet over and you put you do the north side, what happens to the magnet?
The south side points to it.
That's right, the south side points to it. Good job. So I want all of you to put your magnets on this plate. Let's line them up so they're all facing the same direction. And I want you on your worksheet to draw what direction all the arrows are facing. Let's do that for a second. All right, great job. So now we are going to create a magnetic field with this battery and wires. I'm going to attach this wire to the pole, and I want you to see what happens. So now that we've attached the battery, what do you notice about the arrows on the compasses? What direction? That's right. Draw on your paper what direction the arrows were all facing. So now we're going to switch the battery over. We're going to turn it so that it's going the other direction. What direction are the arrows facing now? Draw in your worksheet. So what we've seen here is that we can affect the direction of a compass by creating a magnetic field. And what did we else say? What else did we say had as a magnetic field around it?
The Earth.
That's right. The Earth has a magnetic field. The Earth's magnetic field helps protect us from solar flares that can cause power outages around the world. So that's really important.
Okay, so this is the pinwheel station, which is a lot of fun, mind you. Okay, so first I have a pinwheel and a nail, and I'm going to place the pinwheel on the nail just like this. Then I'm going to make sure that the south end of the magnet, this circular magnet right here, is going to face the bottom of our nail. And in order to find out which side the south side is, we're going to use our red magnet to tell us. So if I place the south end of our red magnet near it, it repels. So in that way we know that this end is the south. So let's go ahead and attach it now. Okay. Now what we're going to do is get a battery, and we're going to have the wire taped to the positive end of the battery. So that way the nail is at the end of the negative end. It'll be just like this. Let me, sorry. Let me try to do that one. Okay, now that we have our nail and magnet set up, we are going to add a battery. So we want the nail, the top of the nail, to be at the negative end of our battery. So it should hold and hang just like this. Now what we're going to do is we're going to have a wire. We're going to attach that wire to the positive end of the battery, and then we're going to touch it to the magnet, and we're going to see what happens. Whoa! Look at that. So, Which direction was the pinwheel going whenever I connected the wire?
To the right.
Clockwise. Yes. So whenever I have the south end attached, facing the end of the nail, it is moving in a clockwise direction, just like that. So now we're going to observe what happens when I switch the magnet's side. So instead of it facing the south side, we're going to face the north. So we flip it and we do the same process. Negative end of the battery, connect our wire to the positive end, and now to the magnet. Now what direction is it going?
Counterclockwise. To the left.
To the left, exactly. It's going counterclockwise.
So welcome to the station. So you guys all have seen magnets now, and we said that magnets have a force. And what did we say that force was called?
Magnetism.
Magnetism, great. Well, magnets have a force field around them. Kind of like if you're a Star Wars fan. And so we're going to look at the force field of magnets. So you have here a magnet, and you have a petri dish, and inside the petri dish are some different colored sands. I want you to try to separate the different sands using your magnet. Could you separate them?
Yes.
Which sand got stuck to the magnet in the petri dish?
The dark
The
one.
dark one.
The dark one, that's right. What pattern do you notice when you look at the iron filings when you hold the magnet next to them?
They stick up on the ends like hairs.
That's right. The iron filings are showing you what the magnetic field looks like. What do you notice about the magnetic field? Is it all the way across the magnet or just in certain parts of the magnet?
Certain parts on the end.
That's right. The north and south each have their own magnetic field, and they are going towards each other.
So, what happened when we had our wires connected to our battery? What happened when we connected it to our metal rod?
The north's pointing in different directions.
Yes, but try to think back to last week's lesson with electricity. So we had our battery and we had our two wires and we had our metal rod. So what did we create?
A circuit.
Exactly, we created a circuit. So the electricity flowed through the metal rod. And what did that cause? Someone said it earlier. What happened to our...
The compasses change direction.
Exactly. So our compasses changed direction. Which direction did they change? So first we had the positive end of the battery attached on top, on the top of the metal rod. And so which direction did they change?
They went clockwise.
Clockwise, exactly. So we're going to go ahead and draw it in on what that looked like. Perfect. Clockwise. And so what happened when we switched it?
They went counterclockwise.
Counterclockwise, yeah, they went in the opposite direction. So what this tells us is that magnets have direction. What else did we learn in the very beginning of our exploration, or the beginning of the lesson? What else did we learn that gave us clues that magnets have direction? Very first thing we talked about.
They have north and south poles.
Yes, exactly. So remember, back to our magnetrix, the opposite ends will attract and the negative or the like sides will repel. Yeah, so that tells us which direction our electromagnetic field moves. Okay. Why do you think that when we just had the metal rod alone, why didn't it change the direction of our compass? When we didn't have any wires or anything attached to it?
There's no electricity flowing.
Exactly. And so when we added electricity, that caused everything to move. right?
Yes.
Yes. Okay, so when we added electricity, we created an electromagnet. Can everybody say that with me? Electromagnet. Awesome. And so we're going to go ahead and post the definition of an electromagnet. There it is. And so an electromagnet is a magnet that only works with electricity. So when we added that electricity, that caused our metal rod to attract different objects. It created a magnetic field. Okay. So, do you think our magnets have to be in direct contact in order to apply a force to other objects?
No, because they weren't touching earlier.
Exactly. They don't necessarily have to. So magnets can repel each other, but that force, or it can attract. And so when it attracts, it's causing this other magnet to move closer and closer to it. So again, what is a force?
Something that causes motion or change.
Exactly. Something that causes motion or change. It's a push or a pull.
Great. So now that we have learned about electromagnetics, like fields, we're going to do a little demonstration with the power of electromagnets. So I have here two different nails that have wires wrapped around them. What do you notice about the wires on the two nails?
One has a lot more than the other.
That's right, one has a lot more than the other. So we're going to try to make a magnet and pick up these paper clips with these nails. Let's make a prediction. Which one do you guys think is going to be able to pick up more nails? The nail with less wires or the nail with more wire?
More.
More. Let's find out. So we're going to attach our nail to our battery and see what happens. Did it pick up paper clips?
Yeah.
A little bit.
Just a little.
Alright, let's do the other nail, the one that has more wire. Let's attach it to our battery and let's pick up some paper clips. What did you guys notice?
Picked up all of them.
It picked up all of them. So was our prediction correct?
Yes.
Yes. The reason why this one picked up more nails is because it has more wire and it's very closely, tightly packed. So now we want you guys to show what you know. So look over the questions and talk about them with your neighbors, and then we will go over them together as a class. Now that you guys have discussed your answers with your table, we want to talk about them as a class. So table number 1, what do you think the answer to the first question is? In the diagram below, the north pointer on the compass will point in what direction? A, B, C, or D?
D.
D.
B.
B. Remember in our experiment, when we put a magnet right next to a compass? What happened when we put the north side of the magnet right next to the compass? Which of the arrows got attracted to the magnet?
If it's the north side, the south side got attracted.
The south side is not attracted, and it's facing east. So what direction do you think the north side is facing?
West.
West. You're correct. Good job. Alright, so table number 2. In the experiment that we performed today, the pinwheel turned because A, B, C, or D?
B.
B, that's right. It turned because of the magnetic force from the current of the battery through the wires. Table number 3. In the diagram below, which pair of magnets will be attracted to each other? It's hard to see. But this says south and north, south,
B.
south, north, south, north, south.
B.
B, yes, B. And why will those be attracted?
Because they have opposite ends.
That's right, and in magnets, opposites attract. So table number 4, let's try to answer these sentences from our word bank. When two magnets are put together, they are attracted to one another if the poles of the magnets are blank. Which answer?
Different.
Different. Table 5, a compass needle points to the north because the Earth has a,
C. Magnetic field.
should say magnetic field, that's correct. In table 6, a magnetic force is caused when blank flows through a wire.
D. Current.
Correct, current. And last table, if the poles of two magnets are blank, they will repel each other.
The same.
The same. Good job.